Hey everybody. Get going here. Pin my screen. Let's close some other stuff. Give me just a minute for everyone to get here. Let's see, do I need to do that? No, I need this thing. One. Here's a link to the attendance document that we've all been filling out. So everyone can go here and do the usual thing. Enter your student ID number, click on the class that you're attending. That would make my life so much easier. Thank you so much. You see that Sanders posted a homework assignment, which we can definitely do some similar examples of that if you guys would like. I have a couple ideas of things to do as far as I watched his previous lecture and he talked about sequences and he talked about difference equations and a couple other things. So if there's anything that really stands out that you guys would like me to talk about, speak up. You can say words, you can type something in the chat. You can turn on your video. I would love to see your faces if you want to show me your face. Eventually, I'm going to get all of you to show me your faces. Or a picture. So I would like to encourage everyone, once again, to, even if you're not going to show a video, that's perfectly fine all the time. But if you could upload a different picture for your Zoom video, whatever the screen is called. If you look at mine, so I'm going to turn off my video for a second. Mine is a picture that a student drew of me when I taught UCCS. It doesn't have to be as fun as my picture, but if you could pick just a nice picture, something so that it's not just darkness up here to look at, I would really appreciate it and make things a little brighter for me. So when you have a chance, yeah, Jersey Shore, all right. Hi, Harold. I like the background. It's very entertaining. Yeah, thank you. I appreciate that. So pictures or on video would be great. There was something else I wanted to say about that. Maybe I'll post something in Canvas to remind you guys to do it. But yeah, just it'll make things a little brighter on my screen. So any questions, any concerns about the material, anything you'd like me to cover? Do I have my volume on?
Could we do an example sequence problem?
Definitely, yeah. So sequences are kind of a big deal, but let me turn my light here. Oh, my light's on. What I kind of think about, yeah. At this point, I would say there's two things we'll probably be doing with sequences. One thing is, which he did an example of in class, which is where you're given like the first few terms of a sequence, and then you have to kind of identify the formula for the sequence. So an example of this could be something like, here are the first 5 terms. Let's say we've got, I don't know, let's make it not too terrible, James. Sorry, I'm trying to make something up that's not so awful. Sure. 4/3, 7/9, 10/27, 13/81, 16/243. And so our job here is to identify the pattern. And definitely watching Sanders do this on his lecture, I feel like he thinks about this very much the same way I do, and I think he'll write problems in the same sort of way, meaning you essentially you're going to look at the numerator and the denominator kind of disjointly, right? They're kind of separate from each other. So looking at the numerator, or the top, as I will often call it, I see 4, 7, 10, 13, 16. And when I'm looking at this, one of the key kind of ways I try to identify what's going on in the sequence is to look at the difference between the terms. So if I look here, I can see that the difference here is +3. The difference here is also +3. All of these differences are +3. So I know the top is going to look like something like 3n. Because when you're writing a sequence, the n thing is always increasing by 1 each time. So if n was 1, I'd get 3. If n was 2, I'd get 6. If n was 3, I'd get 9. But I don't want to get 3, 6, and 9. I want to get 4, 7, and 10. So it looks like I actually need 3n plus 1 for the top. And again, I'm assuming, and it's often the assumption, that we're starting at n bigger than or equal to 1. So if n is 1, I get 4. If n is 2, I get 7. If n is 3, I get 10, and so on and so forth. Sometimes we start at n equals 0. Sometimes we start somewhere else. But for now, this is what I'm kind of envisioning. For the bottom, I don't have quite the same sort of thing going on. Right? I have 3, 9, 27, 81, and 243. And if I try to apply the same sort of thought process here, well, if I look at the differences here, I get 6. 27 minus 9 is 18. 18 minus 27 is 54. 243 minus 81 is 162. And so if I don't see a really clear pattern to start off with, I look at the differences of the differences. So if I look at the differences of those things, now you might already see what the pattern is here, right? You might see that 3 and 9 and 27 and 81 are all powers of 3. But if it's not super duper clear, I like to look at these differences just to kind of see what's happening. So here the difference is 12. Here the difference, let's see, 54 minus 18 is 36. Here the difference, 162 minus 54 is 108. Okay, now here's what I do see in each of these examples, or each of these differences. In this row here, which is maybe what we all want to look at, each subsequent term is 3 times the previous term, right? 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 43. But if you don't see that right off the bat, you can see it in the next row. 6 times 3 is 18. 18 times 3 is 54. 54 times 3 is 162. If you don't see it there, you can see it in the next row. 12 times 3 is 36. 36 times 3 is 108. So if you've got something like this where it's always the next power of 3, you'll always see that the differences are always increasing by a multiple of 3. So here I'm seeing that this looks like 3 to the n, right? This is 3 to the first, this is 3 to the second, this is 3 to the third, this is 3 to the fourth, this is 3 to the fifth. And so in this case, it looks like my a sub n, which I write up over here. So I would write that a sub n is equal to, well, on top I have 3 times n plus 1. On the bottom I have 3 to the power of n. And that's giving me all the terms. So that's one thing we can do with this. So let's do another example. I think there was something else that was occurring to me. No, okay, no. So let's try this one. I'm gonna call it B sub n. Also, for those of you that, so I don't know, I think when people join late, they can't see the previous chat. So if you have joined and you can't see the link I put up there, here is the link again to make sure you all go fill out the attendance Google form. So let's look at B sub n. For B sub n, we're going to do something like, what am I thinking of here? Usually we do these as fractions. We do the first 5 terms. I'm going to make this one, I'll make it interesting. Let's do 5/4, -9/8, +13/16, -17/32, and +21/64. That doesn't look too bad. All right, so again, if I'm trying to figure out what's happening here, I'm going to look at the numerator and the denominator separately. So, and also the alternating part. So if it's alternating, right, if it's going positive, negative, positive, negative, positive, negative, etc., we know we're going to need for the alternating part a negative 1 to the n or a negative 1 to the n plus 1. One of those will start positive, one of them will start negative. If we're starting at n equal to 1, well, negative 1 to the 1 is negative 1. So this isn't the thing I want for this particular example. I want this one, because negative 1 to the 1 plus 1 is negative 1 squared, which is positive 1. So we definitely want that way to start the alternating series. Sequence, alternating sequence, a series of something completely different. And then, again, I'm going to deal with the top and the bottom separately. So for the top, I ignore the alternating, the negative, positive part. I just look at the positive terms. I have 5, 9, 13, 17, 21. So looking at those numbers, what's the difference between each of the subsequent terms? Exactly, adding 4. So if you know you're adding the same thing each time, that means you want that amount times n. So I know that this is going to give me, on top, I'm going to have a 4 times n. But that's not exactly right, right? Because if it's 4 times n, I'm going to get 4, and then 8, and then 12, and then 16, and then 20. So what I have to do is I have to say, okay, well, I know I'm going to add 4 each time, but I want to start at 5. So if I'm starting, if n starts at 1, if I plug in 1, I get 4 times 1, which is 4, but I want to get 5, so I have to add 1 to get 5. And then that should work, because then when I plug in 2, I get 4 times 2 plus 1, which is 9. And I plug in 3, I get 4 times 3 plus 1, which is 13, and so on. So usually I identify how, if it's something like this where it's increasing by the same amount each time, it's that amount times n, and then we add or subtract whatever we need over here so that we get our first term to actually be the right value.
For the alternating, why would it be the exponent of n plus 1 rather than just n?
Because this one we want to start positive.
Okay.
So
If
right,
we wanted
if I did this one, negative 1 to the 1 is negative 1, but I want my first term to be positive.
Okay, so if it was the other way around, we'd use the n?
Say that one time, sorry.
If it was the other way around, we would just use
Like if it was negative 5/4, positive 9/8, negative, yeah, then you would do negative 1 to the n.
Okay.
So it's either one of these, and you pick which one depending on if you want to start with the positive or start with the negative.
Okay, thank you.
And then for the bottom, like so here for the bottom, we could do the thing I did before where we're saying it's differences, but I think we can all see that those are powers of 2, right? 4 is 2 squared, 8 is 2 cubed, 16 is 2 to the 4th, 2 to the 5th, 2 to the 6th. So if I'm starting at n equal to 1, well, I want 2 to the 1 plus 1, and 2 to the 2 plus 1, and 2 to the 3 plus 1. So I really want the bottom to be 2 to the n plus 1. Essentially, when you're doing this, you're kind of trying to make each term have the increasing part show up, right? I want a 1 there, and a 2 there, and a 3 there, and a 4 there, so that I can see what n is going to replace. Just like here, I'm really thinking of this as 4 times 1 plus 1, and this is 4 times 2 plus 1, and this is 4 times 3 plus 1, right? It's the pattern I'm finding where, oh, the 1, the 2, the 3, the 4, that's the thing that n is replacing. Or it's called the index, the thing that's increasing by 1 each time. Here, the 1, the 2, the 3, the 4, that's what's getting replaced by n. So my final result, which I'll write in red over here, is going to be negative 1 to the n plus 1 times, on top we need And I usually write the alternating part out in front. You can also write it on top or on bottom. 4n plus 1 over 2 to the n plus 1. I might put parentheses around that just so you know that that's all the exponent of the 2 there. The other thing he talked about when it came, so I should mention, no, I shouldn't mention. The other thing he talked about regarding sequences was recursive sequences or difference equations, where you can kind of define a sequence based on the previous value of that sequence. And he talked about a first order example where, what's the word I'm looking for? He talked about a first order example where the next term was based on just one previous term. He also talked about a second order example, which was the Fibonacci sequence, where the next term was dependent on the previous 2 terms. So you can look at an example. How do I want to say this exactly? So I'm looking at his homework. Let's do this. So yeah. Let's look at it like this. So let's say we have a population at time t given by n sub t. That's fairly typical notation for this class. And what we know is that each year the population triples. And in the first year, and the population is initially, let's say, I don't know, 40 rabbits. Rabbits actually breed really fast. I did an example in the previous class one time where you started off like 100 rabbits in Australia, and it's actually based on real data, and like a few years later, there was like 1 million rabbits, literally. Like rabbits really make a lot of rabbits. So for this one, there's 2 things we need to kind of focus on. The first thing is that n sub, so the first, and usually if it's a population like this and you're talking about the beginning, we usually don't start at n or t equal to 1, we start at t equal to 0. So I say n sub 0 is equal to 40. And then we're going to write the difference equation. Well, I know that in the next year, the population should be triple the previous year. So I'm going to write that as n sub t plus 1. And I didn't say this explicitly, but I suppose I should point out that t is measured in years. So next year's population should be 3 times the previous year's population. That's not too terrible. And so actually, so there's probably, actually the question on the homework is really simple. That's all he's really asking you to do on the homework is find the difference equation and an initial condition. That seems, no, I guess not. But I want to do more with this because we usually do more. So often what we actually end up doing is finding an explicit formula for n sub t, which he definitely did in the example he did in his lecture the other day. So here's what I like to do. I like to make a little table. So we've got time here and we've got the amount of population at that time. So when time is 0, we've got 40 rabbits. And then each year we're just going to triple. So when time is equal to 1 year, we're going to have 40 times 3, which we could simplify as 120, but it's actually really not in our interest to simplify this. It's going to make it hard to see what the answer is if we simplify. Also, if you just joined, once again, here is the link to the attendance form. Please go fill it out as soon as you can. When time equals 2, it's going to be 3 times as much as we had when time equals 1. So I'm going to get the previous amount times another 3. which, yeah, we could write it as 360, but it's going to make more sense to write it as 40 times 3 squared. That's going to make it easier to figure out what the actual explicit formula for n of t is. Next year, it's going to triple again. I'm going to get the previous year, 40 times 3 squared times another 3, which is going to be 40 times 3 cubed. And I think at this point, we start to see the pattern, right? Here we've got 40, or you could write this as 40 times 3 to the 0th. Here you've got 40 times 3 to the 1st, 40 times 3 squared, 40 times 3 cubed. It's looking like at year t, I'm going to get 40 times 3 to the t. So we could say that the explicit formula here is n sub t equal to 40 times 3 to the t. And that would give you the formula for the amount of rabbits you had at year t. I want to modify this example just a little bit because the question he asked in the homework is actually a tiny, tiny bit different. So I'm gonna keep this example and I'm gonna change one thing. So let's say we still have the same sort of thing. So we know that the population is tripling every year. So we still have n sub 0 is equal to 40, and n sub t plus 1 is equal to 3 times n sub t. But this is actually going to change because we're going to say something else. So population triples. I can spell triples each year. But then we're also going to say due to predation, meaning due to, I think of wolves, but rabbits getting killed by predators. Don't watch Watership Down. It's terrifying. Rabbits dying. Anyway, if you watch it when you're 9 years old anyway, it's terrifying. It might not be as an adult. So due to predation, we lose, let's say we lose 8 rabbits each year. This doesn't seem like a very realistic number. I'm going to change it up a little bit, but let's say we've got that. So now, let me see. Yeah. So really our model now looks like this. So the next year's population is the previous year's population tripled, but then minus 8. So if I wanted to try and find, and I actually didn't do this already, so I don't know if this actually turns out nicely or not. If we want to try and find an explicit formula, things are going to get a little bit weirder. So I've got t and n sub t, and I'm just going to do the same sort of thing. This table I think is really, really helpful to see what the formula might look like. So at time equals 0, I've got 40. At time equals 1, I'm going to get 40 times 3 minus 8. And again, I don't think you want to simplify this. I think that's going to make it less clear to see what the formula is. Time equals 2. I'm taking the previous year's amount. I'm tripling that. So I get 40 times 3 minus 8 times 3 minus 8. All right. Next year, I get the previous year, so all this junk. So it's starting to look kind of gross. It might be actually really hard to find the explicit formula for this. Sometimes that's just the case. We could do a little bit of work here. So I might write this as the following. This is 40 times 3. So I might distribute the 3 and get 40 times 3 times 3 minus 8 times 3 minus 8. And then that's 40 times 3 squared minus 8 times 3 to the first minus 8 times 3 to the 0th, which I know might not seem necessary, but I feel like it is. If I look at this one here, if I do the same thing, so again, this is what I just wrote down there. 40 times 3 squared minus 8 times 3 to the first minus 8 times 3 to the 0 times 3 to the first minus 8. I end up getting, so if we distribute this 3, you get 40 times 3 cubed minus 8 times 3 squared minus 8 times 3 to the first minus 8 times 3 to the 0. So I could probably make a pretty good guess at what the formula for the teeth here is going to be. It looks like I'm getting 40 times 3 to whatever the year is. And then I'm getting 8 times 3, or subtracting 8 times 3 to whatever the lesser year powers are. So I get 8 times 3 squared, 8 times 3 to the first, 8 times 3 to the 0. So if I had to guess, I'm pretty sure this guess is correct. N sub t is going to look like 40 times 3 to the t, and then minus 8 times 3 to all the lesser powers of t. The way I would write that is 3 to the t minus 1, 3 to the t minus 2, all the way down to 3 to the 0th. That's not super important. I don't think you need to focus so much on that. I know the homework question is really just asking you to do this part, to find the initial value and the difference equation. Yeah, that's really it. But it's fun to do more work. Let's do one more. What time is it? Yeah, we can do one more sequence. The Fibonacci sequence is neat. It's not the only sequence out there. You could do any kind of recursive sequence where you can say, let's let B sub, he writes it this weird way. So he writes his like this, B sub n plus 1 equals something like, I don't know, 3 times the previous term minus 2 times the previous term. I think it makes more sense to write it like this. B sub n plus 2 equals 3 times B sub n plus 1 minus 2 times B sub n. Both of these recursive sequences say the same thing. This says the next term is 3 times the previous term minus 2 times the term before that. This says the same thing. The n plus 2 term is 3 times the n plus 1 term, the previous term, minus 2 times the n term, which is the previous term. So either way is fine. To write out some terms for this, you have to know the first couple values. So I could start with, and I'm making this up so I don't actually know what's going to happen. So if I say n and b sub n, let's say when n is 0 and 1, so we know that b sub 0 is, I'm going to say b sub 0 is, that would be dumb. Actually, let's say we did this. This is going to be, I'm going to change this, but let's say we start with b sub 0 equals 1 and b sub 1 equals 1. So then b sub 2 would equal 3 times b sub 1 minus 2 times b sub 0. If that's b sub 1, it's b sub 0. And I would get 3 minus 2, which is 1. So then b sub 3 would be 3 times b sub 2 minus 2 times b sub 1, which would be 3 times 1 minus 2 times 1, which would be 1. And here, what I've stumbled upon is a sequence that's just going to keep giving me back the same thing over and over again. I've gotten to what's called an equilibrium point, where you keep getting the same value back over and over again. That's not very interesting, but it can happen. If we change our initial conditions, we'll get something very different. So let's say I started at b sub 0 equal to, let's make it a little more interesting. Let's say I'm starting at -1 and I don't want to get too crazy here. Let's do that. So b sub 0 is -1, b sub 1 is 1. Then b sub 2, so again, b sub 2, so doing it this way, I'm thinking of n equal to 1 is going to be 3 times b sub 1 minus 2 times, if n is 1, I get n minus 1 there, b sub 0. That's going to be 3 times, let's see, b sub 1 is 1, minus 2 times b sub 0 is -1. So I end up with 3 plus 2, which is 5. And then I repeat. B sub 3 is going to be 3 times the previous term minus 2 times the previous term, which is going to be 3 times 5 minus 2 times b sub 1 was 1. So I get 15 minus 2, which is 13. And you just keep doing this, right? There's no, I mean, for these second order ones, it's a much harder to find the explicit formula. We're not being asked to find an explicit formula, but we can keep going, right? B sub 4 would be 3 times b sub 3 minus 2 times b sub 1, sorry, b sub 2, which would be 3 times 13 minus 2 times 5, which is going to be 39 minus 10, which is 29. Yeah. So that's kind of the idea. And you can keep going here. There's definitely a question like that in your homework where you ask you to find like the 10th term. And you really just kind of have to write it out. I feel like there could be a way to do it using a calculator. No, I don't really think so. Not an easy way anyway. So there were a couple other things I saw on here that I thought were worth mentioning. So he asks this very generally, but I'm going to give you some specific examples. So actually, so there was, let's do this one. I'm looking at, well, I'll just say, don't let number 1 trick you. No, actually, that's weird. Number 1, yeah, I don't, anyway, I'll come back to that. I'm looking at the third question there. So I want to do something similar to that, like compute the inverse of f of x equal to, I'm going to do, sure, x squared minus 6x plus 8 for x greater than or equal to 3, or with domain. And so before we actually find the inverse here, I want to just talk about kind of what we're really doing. So this is a parabola. It's opening upwards. And what's the vertex of this parabola? Well, the vertex, the x-coordinate, is negative b over 2a, which is 3, which is not surprising to me at all because the domain is starting at 3. And usually for these parabola inverse function things, the domain typically starts or ends at where the vertex would be, so you don't have any kind of weirdness. The y-coordinate, which is not so important, if I plug in 3 for x, I get 3 squared minus 6 times 3 plus 8, which is 9 minus 18 is negative 9 plus 8 is negative 1. So here's what I'm actually looking at graphically. The parabola with a vertex at 3, negative 1. But it's only when x is bigger than or equal to 3. So I'm starting at 3, negative 1 here, but I'm only going to get the right-hand side of that parabola. I'm not getting any of this. Which is good, because if I had this, it wouldn't be invertible, right? It wouldn't be a one-to-one function anymore. If I just have this, it totally is invertible. So check it out. I'm going to draw the inverse before I find the inverse. So to draw the inverse, if you know the original function, you just interchange all the x's and y's. So instead of 3, negative 1, I'm going to get -1, 3. And this point here would be the point 4, 0, because 4 is an intercept. Is it? Yeah, it totally is. That would be 4, 0. So I get 0, 4. So that would be my inverse function. This is f inverse of x. Okay, but great. How do we find it? Well, we find it just like we normally would. And I think, so he has some directions on there which are fine. And that's one way that will certainly work. I want to talk about a different way because I think it's better. So how do we find the inverse function? Well, we switch x and y. Well, I should say this, right? This is y here. So we switch x and y and get x equal to y squared minus 6y plus 8. And you can totally use the quadratic formula if you want, but I feel like it's kind of weird. Okay, I'll talk about that too, though. So here's how I would do it. I would complete the square. I would say, okay, this is x equal to y squared minus 6y. To complete the square, I take half of -6, which is -3, and I square it to get 9. But really, I have to also then subtract 9, and I still have that plus 8. So this actually looks like y squared minus 6y plus 9. And then -9 plus 8 is -1. And then the reason I completed the square was so I could write this part here as y minus 3, right? Half of -6 is -3 squared minus 1. I like this better because then you can just solve for y. I'm going to erase my graph. Yeah, no, I'm not going to erase my graph. Solving for y, I get, so let's see, add 1 to both sides. And then when I square root both sides, well, usually when you square root both sides, you get plus or minus. I'm getting plus or minus the square root of x plus 1 equal to y minus 3. So hopefully you guys can see down here, y equals 3 plus or minus the square root of x plus 1. The problem is that's not a function. So here it is. Right here, here is y equal to 3 plus the square root of x plus 1. And it totally looks like a square root function. Right? It looks like the square root of x function. And we shifted it 1 to the left. Oh, 1 to the left. And 3 up. But then there's also this. And this is y equal to 3 minus the square root of x plus 1. We don't want that part, right? That would make it not a function. So our actual answer here, the inverse function, which I should write in green, because that's what I'm using. I would get f inverse of x equal to 3 plus the square root of x plus 1. The way I knew it wasn't the other one, aside from graphically, is because of what they told me about the domain. So they told me in the very beginning, the domain of my original function was x bigger than or equal to 3. But we know that when you find the inverse function, the domain and the range interchange places. So if the domain of this function is x bigger than or equal to 3, then we know that the range of the inverse function has to be y greater than or equal to 3. Which is why it had to be this function up here so that y is bigger than or equal to 3, not this function down here where y is less than or equal to 3. So typically, them telling you the restricted domain means you know what the restricted range is, and your weird answer kind of revolves around that. The questions about this, because I know it's a little bit weird. I do want to talk about how he does it because, or how he talks about doing it, because I'm not exactly sure what he means, and we should probably look at that for just 1 second. So he says to do it by doing the quadratic formula. So here's what I'm guessing he means. So quadratic formula. I mean, I use the quadratic formula, so I guess I'm gonna, oh, I get it, right? Because, oh, that's funky. All right, here's what I think he means, and this is a little bit of a guess. I think what you have to do is you have to write this. Do y squared minus 6y plus 8 minus x equal to 0. So I subtracted the x over so that then I can use the quadratic formula here to solve for y. So this, my a value is 1, my b value is -6, and my c value is 8 minus x. I'm not gonna lie, I'm a little bit worried about this, but we'll see what happens. So the solutions, this is where it's important to remember that when you're solving the quadratic formula, you're getting what your variable here is equal to. So our solution is y equal to -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. My pen is definitely dying. I got lots of pens. I just was trying to get the most out of this one I could. So if I simplify this, look what I get. I get y equal to 6 plus or minus the square root of, let's see, that's 36 minus 4 times 8 is minus 32 minus 4 times minus x is plus 4x all over 2. Simplify a little bit more. You get 6 plus or minus the square root of 36 minus 32 is 4 plus 4x all over 2. Okay, what can I factor out from inside the 4 plus 4x? Gabriella already said the right answer before in the chat. It's 4. I can factor out a 4. But what's the square root of 4? So look, we get 6 plus or minus 2 square roots of 1 plus x. So I factored out the 4. And then divide each thing by 2, and you get 3 plus or minus the square root of, I'm going to write x plus 1, which is exactly the same answer we got over here. Kind of neat, except then you have to decide which one, right? We know it's the plus part. So what I want to say about that homework question he has, question 3 on his homework, is you have to do, so if you're going to do it the way he described it, which you probably should do it that way, I guess, you can't just use the quadratic formula on this. You have to actually subtract x and set it equal to 0 and use the quadratic formula on this. Good to know. That's a little bit tricky. Okay. So.
Excuse me?
Yeah.
How did you get x plus 1?
Because, so, good question. So what I did here, and I didn't really show that step very clearly, is I factored out the 4. So I wrote this as 4 times 1 plus x, like that. And then the square root of 4 comes out as a 2.
Oh, okay.
That's what I did. And the other reason I did that was I knew I was trying to make this look like what I had over here. But then you would have to say that the answer was 3 plus the square root of x plus 1, so that the domain and the range of this matches up with the domain of the original function. There was something else. Oh, I just wanted to mention, for those of you, and there's not many of you, but for those of you who are in FAM's class, I believe is going to be having you enter things on Gradescope for your quizzes using some mathematical typesetting called, you don't really know, it's called LaTeX or LaTeX. You don't really know the name of it. You have to use like $signs. And those of you in Sanders' class, who's everyone else, might have to do this at some point. I don't really know because I don't think he's decided exactly how he's going to be quizzing you or giving you exams. But I posted a video on YouTube kind of showing you how to enter the things in Gradescope. So if that's something you have to do, I would definitely recommend looking at it because it's not super intuitive at first, but it is pretty easy to use once you get a handle on it. So if that applies to you, go check that out. I feel like there was something else. Everyone, one more time. I don't think anyone's come in, but there's the, you know the thing. Go fill out the thing, the attendance form. Last thing I wanted to talk about with the very little time we have left is something like this. So let's say, let me see here. Suppose that, and this is kind of the only real questions we have with log, log, and semi-log stuff. Suppose that when, what have they got here? When a function f is graphed on log paper or plot on a log plot, the result is the following linear equation. Capital Y equal to 3 capital X plus B. So when you see capitals like that, you should think, oh, they really mean I have log of my regular variable Y and log of my regular variable X. And I don't want to actually use a letter there, I want to use a real number like 4. So the idea here is that we want to, and then so the question is, find the actual relationship between lowercase y and x. So if it's log, you'll start off with a capital Y and capital X. You need to replace both of those with log of little y and log of little x. If it's semi-log, you'll start off with a capital Y and the lowercase x, the regular x. And you'll only have to replace capital Y with log of lowercase y. So to solve this, to figure out the relationship between y and x, I'm going to say, okay, my equation is actually going to become log of y equal to 3 times log of x plus 4. And then the whole idea is to isolate y, meaning I have to write both sides as powers of what base? Oh yeah, what base?
10.
This many, yeah, oh sorry, this many. 10, exactly, right? When it's log without a base there, it's log base 10. So I'm really saying, and I'm just going to do this quick because we got not a lot of time. So it's really going to be 10 to the all this equals 10 to the all that. Now, here is what people expect you to do after this. They don't expect you to leave this right-hand side just as 10 to the 3 log of x plus 4. They expect you to break it up and simplify it in kind of 2 steps. First step, I'm going to write this as 10 to the 3 times log of x times 10 to the 4th. And then this part here simplifies further. This is going to be 10 to the 3 times log of x. That 3 can come up as the power of x using the logarithm power rule. So this is 10 to the log of x to the 3rd times 10 to the 4th. And then 10 to the log base 10 of some stuff is just the stuff. So this ends up being y equal to just x to the 3rd times 10 to the 4th. We usually write the constants in front, so I would write this as y equal to 10 to the 4th times x to the 3rd, or I might even multiply that out and write it as y equal to 10,000 times x to the 3rd. That would be the final answer that they really wanted you to write. Okay, so the only difference, so the difference between this and a semi-log is that for a semi-log, you wouldn't have had log of x here, you would have had just regular x to start. And so then when you did 10 to the, on both sides, you would have ended up with x in your exponent and would have stayed there. So I'm going to say this again, I think I said this last time. If you've got a log-log graph that's linear, it becomes a power function where you get x to a power. If you have a semi-log graph that is linear, you end up with an exponential function as your answer, where you've got x in the exponent at the end.
What did the answer say? I'm sorry.
What's that?
I can't really read the first number of your final answer. Is it 10? Is it 10,000?
10,000. Sorry, it's a 1 with 4 zeros.
Okay, thank you.
Sorry about that. So that's about it as far as time. If you guys have questions or concerns or things you want to see, start a discussion thread in Canvas and I will either respond to it or make a video to give you some clarification, whatever you want. If you speak up, you'll get stuff. If you're quiet, you get nothing. No, I'm just, but say things and I will try to make videos for you guys or answer your questions as much as I can. All right, I'll see you. Oh, and I'll try and get your quizzes graded as soon as I can, but there's kind of a lot on my plate right now. So it might not happen until like the end of the week, but I'll definitely get those graded sooner than later. And yeah, take care. I'll see you guys on Friday. Oh, how do I get, oh yeah, sorry, I didn't see that before. And also make sure you fill out the attendance. All right, bye.